Hi, this is Grace Gokey, and I'll be presenting on my espresso grinder design for Project 3. So for a quick overview of this design, the goal is to design a drive shaft, burr mounting, and an adjustment system, as well as to identify the best bearings and support for the system. So to make these geometry choices and the initial design, I first ran hand calculations in MATLAB, and then I backed this up with an FEA analysis done in ANSYS for the first two subsystems. And then so some of the requirements for this design are that the power needs to be between 250 and 500 watts, and that the operating speed is between 300 and 1200 RPM. And then the flat burrs are 83 millimeter in diameter. So as part of this grinder design, it's meant to be used in a commercial setting, and so it's operated constantly for up to 200 cycles a day. So it's important that the design will hold up to this constant use. And then the design should allow for changes to the grind size, just because the consumer, depending on the different coffee beans, may want to change what the quality of the grind, how big or small or coarse or fine the grind is. So before beginning the design, I did some research into the example given, which is the Weber EG1. And this is a commercial grade coffee grinder. It has 80 millimeter burrs, so just a few millimeters smaller than our design constraint. And it has very similar features to what we're working with. So the most helpful thing to see from this design was the operating speeds and the power requirements, which the operating speed was a very wide range from 100 to 1500 RPM. And then the power requirement didn't dip below 315 watts. So I tried to base my design off of this model, which boasts similar features. To decide on the power and speed requirements for this grinder, the geometry of the burrs needs to be considered. So the flat burrs are chosen for this design because of the benefits they provide for the consumer. There's certain benefits to grinding it with the flat burrs that increase the flavor or the taste of the coffee. And so with flat burrs, they do require more power and speed just based on the geometry in order to crush the coffee beans in a similar time. And the feed rate is also slower on the coffee beans being fed into the burrs. And unlike the conical burrs, unlike a conical burr, it relies on inertial forces to remove the grounds from the burrs, where the conical burrs, it uses gravity to drop the grounds out. And so given these factors, the power and speed requirements were chosen to allow for enough torque that the coffee beans are ground quickly and efficiently for the commercial setting, while the RPM is chosen so that the machine does not overheat, which can affect the quality of the coffee as well. So the power is chosen on the higher end and the RPM is chosen more on the lower end mid-range to strike that balance. To design the first subsystem for the shaft design, I used the Goodman criteria, and that's that equation shown on the left, and that uses a factor of safety of 3 and uses a material choice of 1045 steel. I chose this because it's common, cheap, and easy to manufacture. Mostly that material choice is based off of existing practice. So, and then this diameter calculation also includes stress concentration factors for a shoulder and the fillets on their shoulders on the shaft. So using the power and rotational speed from the previous slides, I calculated the torque for these calculations, and the hand calculations are seen in the appendix at the end of the slides because I calculated them using MATLAB, and I came up with a 7.7 millimeter minimum shaft diameter, which the next standard size up from that is 8 millimeter, and this is the chosen size before the keyway addition, which later on in the slides, as with standard practice, I added 10 to 15% onto the diameter to make up for that stress concentration from the keyway. And then the fillet radius from this calculation came out to be 0.8 millimeters. For subsystem 2, I chose to do a key connection. I referenced the textbook example 7.6, I believe, and based on that example, I chose the key material to be G10180, as it is a relatively cheap metal for this application, and then a low design factor of 1.5, and that was chosen with the intent to have the key break before any more important parts of the system, and as a sort of preventative failure mechanism. And so I was working in metric units, so I chose a standard QA size of 3 millimeters by 3 millimeters, and then used the equations from the textbook to calculate the length for preventing failure in shear and compression, compression being crushing of the key. And again, those calculations are in the appendix in the slides showing my MATLAB code. And with this keyway, I added on 10 to 15% of the original shaft size calculated in the previous slide, so ending up with a diameter of 10 millimeters, just to allot for a lot for the stress concentrations due to the keyway. And so for the gap adjustment mechanism, the goal was to get a 0.1 millimeter resolution to adjust the size of the gap for different grind quality. And so using the equations in the textbook, I chose a M80 collar size to fit around the to fit with the burrs used in this design, and then that from the textbook, that size has a 1.5 pitch, which is equal to the lead, and then that is used in the self-locking equation from the textbook, and the frictional constant is taken from table in the textbook as well, and is, I believe, 0.11. And then using that equation, again shown in the MATLAB, the actual calculations are shown in the appendix. It is validated to be self-locking, and then the mechanical advantage is calculated using the equation for how much torque is needed to raise it based on the axial forces, and that is found to be 8.69, so that is in the range that I was looking for, and means that the system is not hard to move for the consumer. And then here is an appendix slide, and here is the next appendix slide for my MATLAB code, and then some of my references.